Alright, hell yeah. So we have the Pathfinder, Olympiad, Physics, and this is the first problem, and I'm going to go over the fast solution, because this video is hella long, and we go over relative velocities. But first, anytime I get these problems, I kind of, try to find a part of the problem where it makes sense. So we have, let's say, just two cars, and they're on a track, and they're racing to another town, and they're both going 60 kilometers per hour. And then a storm hits, and then both have to lower their speeds to 40 kilometers per hour. So I got this in terms of meters per second, because part of the problem is that when car A starts, off, it's going to go for 30 seconds before car B then starts at that, faster speed. And so the first thing we want to know is the distance between these two cars, which is just the velocity of that first car at 16.6 meters per second times 30 seconds. You can see that the units will cancel and we get 500 meters. So this distance will stay the same throughout the entire, time. And to show that, I was just like, well, we can have this storm hit at any location kind of on the race. And so I'm going to say here's the town or the finish line. And I'm going to say this car A basically just gets right up to the finish line. The storm hits. Both cars have to reduce their speed. But at that point, instantaneously, this one crosses. So this one's done. But now B has this now lower speed. It's 500 meters. It's always been 500 meters away from A. And now it has to reach the finish line, get to the time, and it says what's the time interval, what's that time interval. And so I use this strategy of like the units are the equation. I have a velocity here in meters per second. I have a distance here in meters. Maybe you don't know what to do. It's not super intuitive to how to get time. So I have meters per second, and then I have meters. If I multiplied these, it wouldn't make sense. I would have meters squared per second. And so you can kind of just play around with it and see that, hey, I have to take this meters and then divide by meters per second. The meters cancels, the second pops upstairs. So let's do that. 500 meters divided by 11.1 as the speed in meters per second. Seconds pops upstairs, meters cancels, and I get 45 seconds. Which I think is the answer. None of my answers could be, they could be totally wrong. All we're doing is just kind of, trying to make logical steps that make sense to me. I might be doing the completely wrong problem, but I think I'm pretty good on this one. Alright, so now what we're going to do is we're going to go over the more complex part of this problem. It involves relative velocities. So, what is a relative velocity? Well, relative velocity says we can imagine, and cars are cool because you can imagine like maybe you're a passenger in this car and you can look around. And so, and I'm sorry, so car A is first, car B is second. And then in the second situation, we're over here. So even right here, when we're both going at the higher speeds, how we write this is like, hey, I want to know the relative velocities. And there's two ways to write it. We're going to write it like this. Velocity of A with respect to B. So this is going to be, hey, the velocity of A, as measured from this point. So this is the point of measurement. You can also say this as, and then, so this first part right here, you know what I mean? This is what we're trying to analyze, the first part of that. So we have velocity of A, that's what we want to analyze, and then we have this slash term and then B. It means like measured from B. It also means velocity of A as seen from B. So that's kind of interesting because we want to know the velocity of A, but we actually as seen from B. So we get into this car, we're a passenger in this car, we're looking at car A and we're trying to see if it's has velocity. But because we're both going at the same speed, it appears not to be getting any farther away from us or any closer to us. So its velocity of A as seen from B is going to be 0. So that's kind of that way to look at this equation. Okay, two more ways to look at this equation. You can just kind of in a general sense, this might be the most easy. Like, what's relative velocity? Comes up a lot in problems where you're just like, well, like, what if I just subtract? I know maybe the velocity of A and I want to subtract the velocity of B. And this problem is perfect for that because it's something that we just totally take for granted. We just, just know that this car has a speed of 16.6. Once this second car B, hits the racetrack, it also has a speed of 16.6. And the difference between them, this velocity minus that velocity is going to be 0. I think we can kind of see that. So this is velocity of A minus velocity of B. And for whatever reason, that's just going to be the relative velocity. But how do we write this as, in kind of a funkier form? Because we get into problems where you're just like, well, you have to say the velocity of A, sure, it's 16.6 meters per second, but as seen from what? You know what I mean? So maybe that's the shirt I should say, like, as seen, oh, I shouldn't be writing this, from what? You know what I mean? And I don't even know if I said that in the video like that, but yeah, it's like, cool. So you have a velocity, but as seen from what? You know what I mean? Because let's go back to, you were an observer in this car observing velocity of A. So this is kind of one of the Newtonian laws, is that you can't sense velocity. If you're in an airplane, you really can't tell how fast you're going. So if you're a chunk of mass and you have a constant velocity, you're just not going to be able to tell. But so you're not going to be able to know your velocity. Sure, it's 16.6. And this velocity is 16.6, but relative what? Relative to what? Relative to the earth. To the ground, you're going at that speed across the ground. But when you're in a passenger in this car, maybe you can't tell how fast you're going, and it looks like this isn't like coming at you or going away from you. So relative, it looks like that has 0 velocity. So we have to pick this point on the ground. And I'm just going to call it point O. I'm going to say like maybe that's the starting line of the race. And so you can either look at this picture or this picture. So I'm going to say, hey, this relative velocity is that velocity of A as seen from B. This is also said velocity of A with respect from B. And I guess the third way is velocity of A. What you're interested in measured from B. Cool. And again, if you're in that car and you're trying to measure this person's velocity, I mean, it just ain't happening. Just from a colloquial sense, it doesn't look like it's speeding up. And cool. So how do we say this? Velocity, the relative velocity is just velocity of A minus velocity of B. But then what, like as seen, what is the velocity of A and velocity of B? As seen from what? So we say it's velocity of A as seen from, point O, like the starting line, cool, and minus the velocity of B as seen from the starting line. Now, you can move the starting line anywhere. It just has to be a point that's like, in this case, it's like your fixed point. Cool. So, but yeah, that's the more, so that's getting to be a more technical equation. All it's saying is like, hey, we know the relative velocity is a difference between the velocities. Here's kind of like the quick way to do it. But we see that the difference between the velocities, we also have this kind of like second term. It's just like, sure, it's the velocity, but as seen from what? So keep that in mind. Okay, and now here is the technical way to write this, and then we'll get on to the video. But because this is, I'm taking the MIT Dynamics course. You can take it for free online, and we'll see how far I get into it. But just even the first lecture, this is all they go over, and it's a mind trip. But it's not too hard, but it requires you to play around with it. So at the end of this video, I try to spend like the last hour, I don't know how long this video is, but I try to play around with this. And I want to make mistakes so I can say right thing, so I can point out those mistakes, correct them, and then say more right things and say them quicker and more accurately. Okay, so we have the starting line, we have the two cars, and Oh, yeah, yeah. So it's from this equation. Well, we'll get that to that in a second. But you can rearrange this equation to get to that. Just, know that. But then I'm just going to say, hey, we're going to have a third way that should be intuitive to figure out what the velocity. And then this one we're not too interested in the relative velocity. All we want to know is the velocity of A with respect to O. But these are for problems where maybe maybe this isn't intuitive. I just don't know what the velocity of this is because, maybe we'll get to that in other problems down the road. But that's kind of that's the classic, is like we want to know this velocity in terms of, in terms of the starting point. We want to know how fast that car is traveling down the road, but for whatever reason, we maybe just don't know that. And so we use this equation. We say, well, maybe I know the velocity of B. And so I'm going to say, this is the thing that I want. In the end, I want to know the velocity of A measured from O. Or if I'm a person at O at this starting line, I want to see how fast that car is moving that way, And so, but I don't know. But maybe I know the velocity of this. So I want to say the velocity of B. Maybe I have, okay, so here'd be an example. I have a radar gun that can't detect this car is too far away. But I can use a radar gun to detect the speed of this car. And then I got a walkie-talkie. So I say, hey, I want to know the velocity of this car with respect to where I'm standing. So we have the velocity of B with respect to O. And then how am I going to use that to find the velocity of A? Well, I'm going to say, hey, car B, from my walkie-talkie, how fast is car A moving relative to you? So that's kind of a cool way to do it, because you're just like, you go from one point to another. So if I wanted to know, let's backtrack a little bit. If I wanted to know how fast car B is going, I need to start at point A and then make a measurement of how fast car B is going. Cool. If I'm at point B and I want to know how fast car A is going when I'm in car B, I have to take my measurement from car B. So that's, I don't know, I'm trying to find different ways just to make this equation more intuitive. But you start from here, you want to go from here to there to there. But your first one's going to be velocity of B with respect to O. Come to this point. Then it's going to be velocity of A with respect to B. And this term is our relative velocity. So we went through that whole process just to be like, oh, we have to know our relative velocity. So again, the velocity of A as seen from the starting line is the velocity of B as seen from the starting line plus the relative velocity, the velocity of A as seen from B. But in this problem, these two cars are pacing each other, going the same speed. Even when the storm hits, they have to reduce their speed simultaneously, so they're always traveling the same speed. So the relative velocity between them is going to be 0. Alright, so hell yeah. So that's enough of this. But I'm just satisfied. I wanted to break this down and to be like, well, what do we just kind of, what can we do from observation? Because we can, like in this problem, the relative velocities are 0. Other problems, there might be, hey, this car's car A. Let's leave it at this. So we're going to say car A and then car B. Car A is moving at 1 meter per second this direction. This is going to be the positive direction, this is going to be the negative direction. Car B is moving at 2 meters per second. Okay, so now let's find and let's spell this out. We want to know relative velocity of what? Velocity of A relative to B. Velocity of A as seen from B. So let's get in car B. We're going faster. This car is going slower. So it looks like this car is coming this way. This is the negative direction. So in this, we would have, this is going to be negative 1 meter per second. So this is from observation. And maybe I should pull out a second sheet of paper just so we can kind of we can probably run through them all. But cool. So that was velocity of A as seen from B. It's negative 1. So now let's do velocity of B as seen from A. From this observation standpoint, I want to know the velocity of B when I'm measuring it from this car. So this car is moving this way, kind of slow. This car is moving fast. So it looks like velocity of B is in the positive direction, and we got positive 1 meter per second. Cool. So that was the observation. Sorry I don't have very much room, but now let's go from the difference, the relative velocity. And again, if I want to know the relative velocity of A with respect to B, I take A minus B. So 1 minus 2 is negative 1. Cool, that was easy. So this idea of difference, I think, is more likely how we understand relative velocity. There's a lot of physics problems where you're just like, well, I need to take the difference between those two numbers. But you can do it in the opposite sense. But sometimes that just yields you, just a sign change. So if I want to know, well, what's the relative velocity of B compared to A? That's going to be 2 minus 1. That's going to be positive 1. Cool. So now let's do it from this inertial reference frame. I want to know, from this perspective, we would have the two equations. We also want to know the velocity of B with respect to O. And then let's say in this, we don't know what B is, but we do know what A is. So cool, I'm going to start there. I'm going to say velocity of A with respect to O. So I know its velocity. Now I'm going to be like at A, and I'll be like, hey, what's the velocity of B? So plus, what's the velocity of B as seen from A? So cool. I want to go from O to A to B. So I want to know the velocity of A with respect to O. Cool. Once I'm at A, I want to know the velocity of B with respect to A. And let's see how that was similar to this one. I think this one was more intuitive because they're all in line. I want to know the velocity of A as seen from the starting line. I just want to know the velocity of that car. So I'm at the starting line. I measure the velocity of this car with my radar gun. Cool. With the walkie-talkie, I was like, hey, what's the speed of car A measured from you? It says 0. Cool. Now I know that the velocity of, and if this is 0, hey, the velocity of this car is the same as the velocity of that car. But now with our little demo, let's do this problem first. I think so we have our point O, and we're going to say velocity of B. So if I'm the person here measuring this speed's car, it's 2 meters per second. Cool. Globally, what I'm interested in, I want to know the velocity at A. But I'm at the starting line with my radar gun. I'm like, hey, I measured that as 2 meters per second. Get on my walkie-talkie. So now we do this one. I'm at B, so this is where I'm at, and I want to measure the velocity of A. Cool. I was like, hey, can you measure that velocity? And it's like, yeah, that car's coming towards me at negative 1 meter per second. Sweet. So I have 2 minus 1, and I can know the velocity at A is 1 meter per second. Cool. Let's do the opposite and finish this, and then get on with the video. But this is where you want to be, because this is kind of the elite level, and it's confusing. But I think observation, difference, inertial reference frame, that's kind of, no one does it that, I'm trying to find ways to teach, and this is kind of a cool way to, all right, let's which one do we want to do? We want to know the velocity of B. My radar gun, for whatever reason, can only measure distances far away. So I know velocity at A, and I measure 1 meter per second. And then I get on my walkie-talkie to this car at A, and I say, hey, how fast is, so I'm at A, how fast is velocity B moving? And it's like, well, it's catching up to me. It's going in the positive direction of positive 1 meter per second. Because I'm traveling slow, it's traveling fast. I think it's going in the positive direction. So cool. So I have, I measured this velocity at 1, and then I got on my walkie-talkie, and they said velocity of B was 1 compared to that car A. So the velocity of B has to be 2 meters per second. But yeah, holy hell. So also watch the end of this video, because man, we just struggle to like, hey, what are we talking about? But this is kind of the 3 things that I think is important when dealing with relative velocity. But the take-home point is like, this is only needed when you're getting into advanced dynamics. But it was just fascinating that at this MIT kind of lecture series, it was first day lecture. That's what the professor went over. And in my college, you know what I mean, not to name names, but I don't know. Like, I went to college 15 years ago, or maybe longer, about 15 years, and I can't remember how I was taught. You know what I mean? I can only remember that it's a struggle. Like when you're in lectures, like you can only get so much information, and so I don't even know if they taught us this way. You know what I mean? But I don't think so. I think like this. There's pros and cons of like so the first lecture at this and this is free online. This is the engineering dynamics course, and it's fairly, you know, it's a sophomore level course, but man, do they teach it from a technical perspective, where I don't think you're going to be able to take that technical perspective and right away apply it to simple problems. It's like, I don't know. I think you need to spoon feed yourself simple concepts. I don't know how to learn. I don't know what the best recipe is. Like, I'm going back and wanting to learn the technical recipes, but it's good because you'll see that I have a foundation to do some of these problems just from a, hey, like let's find an extreme and let's figure out, you know, what makes sense. And then once we do that, then we can work back and see if there was an equation involved. But when it comes to relative velocities, it's like, hey, you didn't have anything. You had a relative velocity of 0, so there was no equation. How do you go from 0 and then just, you know, and then derive these two equations? I don't think that's humanly possible. And so this is one of those where, and down the road, I'll try to involve more of this inertial reference frame equations, just because it takes practice, and hopefully hopefully I mess up and get better. So all right, so now for the rest of the video, thanks for joining me, and hell yeah. Alright, hell yeah, we have Pathfinder, JEE, Physics, and this is the first problem. I don't know if I've already done this one, apologize if I've already done it, but, well, I'm going to be motivated to maybe go through and do these in order. I don't know, because, and it's alright to get hung up, and so, that's going to be the plan, and let's go for it. Let's read this. From a town, a car starts at regular... See, I'd never read, because I just have ADHD. I just want to stop right now. But anyway, so let's not. So we have... okay, so with 30-second intervals, because the second I start reading it, I'll just space out. And then people are going at a constant speed. And then at some point, the cars simultaneously have to reduce their speed to 40 due to bad weather. What will be... Oh, see, even that. You know what I mean? Does this mean that, hey, if I have two cars going, and this car went 30 seconds later, this car, and then all of a sudden bad weather happens, do they have to both reduce their speeds at that moment? Because I read this wrong the first time, I think. So, yeah, so it's like, that's my biggest problem is comprehension. I just want to solve the problem I want to solve, but that's usually not what they want me to solve. Anyway, alright, so what will be the time interval between the arrival of the cars once they get to that second town? At the second town during... Yeah, so hell yeah, I think we should read it all the way through. From a town, cars start at regular intervals of 30 seconds and run towards another town with a constant speed of 60 kilometers per hour. At some point of time, all the cars simultaneously have to reduce their speed to 40 kilometers per hour due to bad weather conditions. What will be the time interval between the arrivals of the car at the second town? And the bad weather continues, so they never increase their speed once it decreases. Okay, so let's do this. Let's see, cars start. So the other part of this question is cars start at regular intervals. So the other thing that's not said here is that are all the cars actually on the track? Like, have they actually started? Because if I have two cars, did both cars actually start going? And sometimes, so this is the process of coming up with the extremes. So I'm going to say, the two extremes that I can think of is, let's say, the first car basically gets right to the finish line, you know what I mean? And then the bad weather starts. Cool. So this car immediately reduces their speed to 40 kilometers per hour, but at that point they cross the finish line. Okay, cool. 30 seconds earlier, and what would 30 seconds earlier be? Well, let's go to the start. So this car is going to start at a speed of 60 kilometers per hour. And this is where we almost need to get this in seconds. So let's do that. We're going to do 60 kilometers. And right now I can just say this is 6,000 meters. I'm going to do that one. But, I mean, factor label would be like you would do it like this. 6,000 kilometers. Sometimes it's good just to put 1 hour down here. And then we're going to be like, hey, 1 kilometer is 1,000 meters. And, we can do factor label one step at a time. And this will give us 6,000 meters, 1 hour. And now we have to change hours. So we have 6,000 meters per hour. 1 hour is 3,600 seconds. And we can even do this one in our head because I don't know if we can, but we can do the first part. 60,000 meters per hour. 1 hour is 60 minutes. Cool. So now I can say that this is just 1,000. So this is 1,000 meters per minute. But now I would have to say 1 minute is 60 seconds. Maybe I don't know how to do this. I can at least get rid of 1 0, and I'm going to have 100 divided by 6. Now, to make, if you can get this as like a multiple of 10, then you can actually do the ratio a lot easier. I've been doing this is going to be 100 divided by 6. It's going to be a bigger number than 1. So let's do this like long division style. I'm kind of into long division right now. And it's even, I even forget what number you put top and bottom. So I don't know, just do it both ways. But it's just kind of fascinating. You put the top number in the division sign. But heck yeah, I always do this because this is going to be like my decimal place. But I don't really want to write the decimal place in. Sometimes that confuses me. But we have 6, and then 6 goes into 10 one time, and then we're going to have 4 left. Bring down the 0, and I don't know, what is this? Can we do it 5 times? Heck yeah, that would be 5 times 6 is 30. We can do it 6 times. So we got 36, and now we're going to bring down another 4. Okay. And then the pattern repeats. 36, bring down a 4. So this is going to be 16.66. And maybe we could have got there. It's just kind of fascinating how, like, you do one thing, and then you go back and be like, oh, yeah, no duh. This is going to be, we can factor out downstairs, we can factor out 3 and 2. And this is kind of an interesting way to do it. So we would have 100 upstairs, which is a factor of 50 times 2. I usually don't do it like that. What I would say is just like, okay, I want to change this to 3. I divided by 2, so this is going to be 50 divided by 3. So this is also, this is why my videos might be interesting, because I don't mind going slow and kind of going over all the things that I should have done. Because it seems like you only have one opportunity to go from like, hey, oh yeah, no duh, this is 50 times 2 and then 3 times 2. I would have never done it this way. I would have just gone right to here. But then if I went to here, it's just like, well, how did I get here? Well, I took 100 divided by 2, and then I took 6 divided by 2. And then why could I have done that? Well, is because 100 is 50 times 2, and 6 is 3 times 2. And it's just kind of fascinating that these are the, we're doing the same thing here. We're taking 50 dividing by 2, and we're taking, oh no, I don't know what the hell we're doing. Yeah, I have no idea. But anyway, so cool, let's move on. Sometimes it's good to learn one thing, but sometimes you can get down a rabbit hole of like, I have no idea. Okay, so we have this value. This is going to be 50 thirds. This is the reduced form of meters per second. So we have 16.6 repeat meters per second. This is our speed. Cool. This 16.6 is 60 kilometers per hour. If it doesn't feel like it, that's for darn sure. But I guess 16.6 meters, that's quite a ways. So let's just back this up. There's 1600 or 1609 meters in a mile. And so if we do 1609 or just 1600 divided by 16, we get 100. And it would take 100 seconds to go a mile. Cool. If it takes 100 seconds to go 1 mile, if it takes 60 seconds to go 1 mile, we're going 60 miles per hour. See, I'm just in America, so it's really hard to convert to kilometers per hour. But what this says is that it's going to take longer, so we're going slower than 60 miles an hour. And we might only be going about 40 miles per hour, or even less. This is halfway even. So we might be going about 35 miles per hour. Say we're just going 30 miles per hour. And so, or 40, you know what I mean, is 60 kilometers an hour. You know what I mean? So that's it's so interesting just to get used to working in a different speed. On my speedometer in the car, if I am going like 50 to 60 miles per hour, this is going to line up with 100 kilometers per hour. So I do remember that that's like kind of the one thing I do remember. The other conversion is like if I run a 5K, that's going to be 3 miles. So 5 kilometers per hour is the same thing as 3 miles per hour. And so we have this ratio of maybe 5 thirds. Maybe I don't even know how to use it, but I just know this has to be the larger number. And then, so if I convert to miles per hour, it's got to be a smaller number. So, just multiply by 3/5. So 60 times 3 divided by 5 is 36. So we got 36 miles per hour. And maybe this 3 over 5 is kind of something I should always have in my pocketbook of like, yeah, you remember running a 5K and it was about 3 miles, or synonymous with 3 miles actually. I mean, even though it's just a little bit more than 3 miles. So cool, we're going 36 miles an hour. And then I guess that's also, and then if we're going 36 miles per hour, what's this in meters per second? It's just going to be divided by 2. 36 divided by 2 is 18. And so, hell yeah, we have another check on reality that this 16.6 meters per second is the speed that we're traveling. And even right now, I'm slowly, even though like doing word problems, it's not real life, but it's slowly, now that if I ever see 16, meters per second, maybe I can visualize first of all, it's really hard to visualize going 16.6 meters per second because there's no cars has a gauge that's going to be in meters per second. So then I just have to basically say if I'm going 36 miles an hour, okay, and even that, change this to 35 miles per hour in all of our streets. Most of our streets, our faster ones, are 35 miles an hour in America. And so I can just now, next time I'm driving, hey, now I'm going to remember to say, hey, I'm going 16.6 meters per second. And I don't know, that's the only way you're going to start burning that into your brain to get an intuition of units. Because like I said, because we don't have speedometers that are in meters per second. Neither does the rest of the world. It's all in kilometers per hour. Alright, hell yeah. So we're done with that kind of tangent, and now we can kind of get back to our speeds. So if this is 40 kilometers an hour, well, I can just say that's 40 times 3/5. So this is about 24 miles an hour, but let's do it 100%. So we're going to have 4,000. We're going to divide by 3,600. Sweet. 60,000. Sorry, 40,000 meters per hour divided by 3,600. This is going to give me 11.1 meters per second. Okay, sweet. So now we have our two speeds, and so I'm going to put those in my calculator. I'm going to store this one is alpha. I don't know. Sometimes I like to. Okay, so we're going to do this 16.1. You have to store them as some letter. So we have 50 divided by 3 stored as alpha w. Cool. So this speed is our initial speed. This speed is our reduced speed. So we have alpha w in our calculator, and then alpha v in our calculator. Okay, so let's get back to the problem. So we learned a lot about this. I mean, this was kind of an important thing of just like, hey, do you know anything about 60 kilometers an hour? Does that ring a bell? And I don't know, I've seen some longboarding videos of people going 60 kilometers per hour, and they're claiming that's kind of fast. And I would agree, 36 miles an hour on a longboard, this seems pretty smoking. Cool. Now, if you're going 40 kilometers an hour, hey, that's only, let's see, what was that? 40 times 3/5. That's only 24 miles an hour. So maybe you're skiing. If you're skiing, you can easily go 40 kilometers an hour. Okay, so I'm slowly, kind of making scenarios that I'll totally forget, but at least trying to make those connections to speeds that you do know. All right. So the first car starts off and it's going 16.6 meters per second for 30 seconds. So now the question is, how far did it go? If it went 16.6 meters in 1 second, it's going to go times 30. So we're going to go 498 meters. And this is where I say the units are the equation, because let's say I have this speed in meters per second, and then I have this time in seconds. Like, what do I do to these? I just multiplied them. And you can see that seconds cancels, and I get a quantity in meters. And just know that these three things are an equation. You know what I mean? This is going to be very helpful. I'm going to do it. Like the second I start doing electricity, which I've not done any circuits problems, since college. And I'm very reluctant to do any, but still, you still have an equation usually of 3 different things. You can rearrange this equation any way you want. So let's do it. Let's just bring the seconds downstairs. So we have a distance in meters, and then we have a time in seconds. Oh yeah, and then it's like, no duh. That gives us our velocity. Now, let's bring this one downstairs. That's kind of the more interesting one. If we have a distance in meters and we divide by meters per second, hell yeah, seconds pops upstairs and we get seconds. So this is also a very good strategy. Anytime you have an equation, yeah, sure, you're using it to solve one thing. But if it's an equation of 3 different things, you can rearrange this equation 3 different ways to solve for the 3 other things. So you have 3 total things you can solve for. Okay, hell yeah. So, so this is going to be 498 meters apart. So I'm going to use this distance to go back to the scenario where right at the end, so here's the finish line, we're going to say the storm hits on this first car and the second car, and their distance is 498 meters apart. And so both these cars has to simultaneously slow down. And but the second this car slows down, instantaneously it crosses the finish line. And now this car has a reduced speed of 11.1 meters per second, and it has to go a distance of 498 meters. And so now, I'm so glad I did this, because we have units of meters per second and units of meters. What could we like, there's really only one thing that we can know from this that makes logical sense is, you know what I mean? If we have meters per second, and we have if we multiply these, we're going to get meters squared per second. That's not what we want. And so we're gonna do that thing over here. Oh, well, this is kind of different. Oh, never mind. No, we're going to take that meters and then divide by meters per second. And that's going to, seconds is going to pop upstairs, meters are going to cancel. Sweet. So let's do that. So now I can just shut off my brain, even though we should go back to be like, hey, I have 498 meters to go, and I'm going 11.1 meters per second. So every second I'm going 11. Let's just say I'm going 10 meters per second. And so every second I'm picking off 10 of these. And so I can change this to 500 meters. And so let's say this was 10 meters. You know what I mean? Cool, I would get there in 1 second. Let's say it was 100 meters. Cool, I would get there in 10 seconds. And so it looks like I'm going to get there in 50 seconds. And so that is the kind of the intuitive process of like, yeah, we kind of know you're going to multiply two numbers or divide two numbers, but it's just good to have kind of a double check. So now let's go back to our equation of, we're going to have this distance divided by that velocity. So we have 498 divided by, what's alpha v? Yep, so 498 divided by alpha v, and we get a time of 44.82 seconds. Cool. So what will be the time interval between the arrival of the cars at the second town during the bad weather? Well, I would say it's 44.82. That's close to 45. And so just right off the bat is like, this is one scenario where I can guarantee that if this car, due to bad weather, has to reduce the speed and then instantly crosses the finish line, this other car still has to travel at that slower speed. And so even for this, I think I've learned enough from this video where it's just like, I'm totally satisfied. And this is what I'm going to do. This is kind of my strategy for physics problems, is like, hey, is there a way to, you know, kind of take things to the extreme? Sometimes that helps. Sometimes just like setting up the problem with one example. Because sometimes with this problem, it's like, hey, we have a string of cars that are going towards another town. Everything's got to slow down instantaneously. And so this is fascinating because I was so, and we're going to continue on with this one. I was so, but I do have to take a little break. Alright, hell yeah. So I'm back, and let's grab a fresh sheet of paper. And so for this problem, we have that initial speed of 16.6, repeat, meters per second, and we're reducing our speed to 11.1 meters per second. Heck yeah. Now even right here, you know, if you can make the problem anything you want. You could just change this to 5 meters per second. I mean, this to 10 and this to 5, or this to 15 and this to 10. Sometimes that's useful, but we'll keep at it like this. All right, so let's come up with some more scenarios. We're gonna say that the first car goes for 30 seconds. At this 16.6, we said that was wait, where did I get? Oh, yeah, so this should be right on 45. I must have used my calculator 16.6 times 30, and so, but no, we're 16.66 times, sorry. You know, we have a bunch of them times 30, so we basically are, yeah, so so we have alpha W times 30, so we're traveling in that 30 seconds a distance of 500 meters. Cool. Let's say right here, the second this car gets on the track ready to go, the storm hits. And so now this car has to reduce its speed to 11.1 meters per second, and this car has a speed of 11.1 meters per second. So they're going to travel at the same speed all the way to the finish line. This first car is going to finish, and then the second car is going to have that 11.1 meters per second, has to travel 500 meters. And so, you know, how do we get time? well, time is downstairs on this one. We got to cancel meters, so we go meters, cancels, meters per second, and we have 500 divided by 11.1. So we have 500 divided by alpha V. So this is alpha V in my calculator, this is alpha W. And so cool, we get 45. So 45 seconds will be, so that scenario, the storm like happened right off the bat. Cool. So now let's do a scenario that's kind of in between, just so we're on point. We're going to say that the first car goes for 15 seconds. Cool. At the speed of 16.6 meters per second, the storm hits. Cool. So now this car traveled a distance. How do we do that? Well, it's going to be 16.6 times 15. That's going to be meters per second times seconds. This is going to give us alpha W times 15. So this car traveled 250 meters, and then the storm hit. It has a new velocity of 11.1 meters per second, and it can travel for another 15 seconds before this other car starts on the track, and it is in the storm, so it has to travel at a speed of 11.1 meters per second. Alright, so if this car travels at 11.1 meters per second for 15 seconds, that's alpha V times 15. It's going to travel for 160. Now, is this right? I don't think that was right at all. So we have, again, meters per second, and we have seconds. What can we do to these? Well, no, we're right. We can just multiply them, and we're going to get distance in meters. Okay, so we have 11.1 meters per second times 15 seconds. And that's going to give us 166.6 meters. I'm going to store that as x. And so now this car is 250 plus 166 meters. So this is going to be a little bit different, I assume. And so yeah, that's going to be the difference between these cars, and has to be, because we traveled real fast. And then, okay, so when these two cars get to the finish line, they have this distance of plus 250 of 416.6 meters apart. This one crosses the finish line. This has a speed of 11.1 meters per second. So the time value is going to be different. So this is one scenario where we're kind of proving to the problem statement that all cars have to be on the track. And so it should have said that. I imagine, unless I'm doing something wrong, that's the tricky thing about math and physics problems, is like you might be assuming you're doing something wrong at every step. That's why it's just like solve the problems you want to solve and see if they match. Okay, so let's continue with this one. We have this distance in meters. We're traveling at this speed. We have to divide these, so meters will cancel, seconds will pop upstairs. So we store this as, I'm going to store this as alpha y, and so we have that 416 divided by 11.1. And that's going to be a speed of 37.5 seconds. So, cool. And so what, like how, yeah, so that might be, I mean, if this thing gets 15 seconds, because we said if this car went 30 seconds and then both cars were in the storm, they're going to be evenly spaced at 30 seconds. Or maybe that's not true. No, I don't think we've done that one. Okay, so let's say this car goes for 30 seconds at 16.6 meters per second. So that's going to be alpha W times 30. It's going to go 500 meters. And then both hit the storm. So now both have a speed of 11.1 meters per second. Cool. And so, and when they get to the finish line, they'll have this same distance of 500 meters. I thought we already did this one. And what's the time? It's going to be 500 divided by alpha V, and we have 45 seconds. Okay, So now, so yeah, so the scenario that you can come up with right off the bat is like, hey, let's say this first car starts off, but then the second it starts going at oh no, this will be interesting too. I mean, the second this first car gets on the track, the storm hits. So its speed is 11.1 meters per second. It goes for 30 seconds. And then the other car starts. So now it's here going at 11.1 meters per second. The other car is going 11.1. And this only went, if it went 11.1 meters per second for 30 seconds, it went 333.3 meters. And then when you get to the finish line, we only have 333.3 meters, and we have that speed of 11.1. And so we're going to divide by alpha v again, and these cars will be 30 seconds apart. So there's a scenario where if this car gets right on the track and the storm instantly hits, the separation between the cars would be as low as just 30 seconds. But if this car gets all the way, into its race, and then the storm hits, and this car hits the track, and that can be part of the scenario where this car gets 30 seconds out, just a little bit more. This other car hits the track with a speed of 16.6 meters per second, but just instantly gets hit with the storm. Then they both have to reduce their speed. You know what I mean? So if you do that kind of instantaneously, when you get to the finish line, you'll have this 500 meters, so it'd be 500 divided by this speed, alpha v, and we'll have 45 seconds. So that's the scenario that's probably most likely, and that's the scenario where both cars are actually on the track. So that's the only part of this problem that it doesn't say. It doesn't say like how many cars. Yeah, so that's fascinating because it makes it seem like there's like an endless stream of cars traveling from a town at regular intervals of 30 seconds towards another town. But yeah, we just came up with two scenarios where that speed is going to be different. This kind of halfway is going to be 37.5, and we're kind of learning. The speed will be in between 30 to 45, and is halfway 37.5? Yes, it is. So depending on how far this car gets before the storm hits, is going to determine this speed. And even right there is just like, I would probably have to say, let's say this car gets 20 seconds, and then the storm hits. Like, it's kind of fascinating. Could I intuit that one? Now I'm going to try. So the question is like, hey, what if the storm hits earlier or later? How is that going to adjust this speed? So if the storm hits, if the storm hits later, these cars will be farther apart. And farther apart meant that separation of 45. So if I'm like right here, where I'm going to have a separation of 40, if I'm right here, it's 37.5. If I'm really close, it's going to be 30, so 35. So now we have a visual representation of the first car getting on the track at that higher speed, the storm hitting within that 30-second interval, and then, that car having to slow down for the rest of its, up to 30 seconds, then the other car hops on. And now they're both going the same speed, but that distance is going to be somewhere between this high end of 500 meters and the low end of 335 meters. Cool. Alright, so we're going to do the problem one more time and see if we can gain any equations from it. Because these problems are part of relative motion, which I don't know. Like, I'm bad at deriving equations of relative motion. So now I'm just going to say there's two cars. We have a top speed of that 16.6. That's going to be alpha W. And then we have a lower speed of 11.1. That's going to be alpha V. we're going to say for sure both cars are on the track, and they're 30 seconds apart. So here's car 1, and then here's car 2. And then the storm hits at some point down the road, and it hits simultaneously both cars. Okay, but up to that point, these two cars are going 16.6, and there was a 30-second interval between them. So the distance in between these two cars is the same thing as saying, hey, this first car is going at a speed of 16.6 meters per second for 30 seconds. So how far, what's the distance it gets away in meters? And we see the units on this are just multiplying both these numbers. So it's going to be alpha W times 30, alpha W times 30, and we get that 500. So 500 meters. Cool, so we got 500 meters here. The storm hits. Now they both just have to reduce their velocity to 11.1 meters per second. Now, if that happens simultaneously, does this distance between them change? And the answer is no, because they're both speeds. So yeah, yeah, it's kind of fascinating. All right, back to it. So yeah, and this is kind of interesting. Like if you're in a race and then you're kind of running and there's someone up ahead. Now, if your distances don't change, that just means that you're traveling at the same speed as that other person. So if you're just like, hey, like I just want to stay with that person, and I want to make this distance the same. Well, that person could speed up, speed up their speed, but you're going to do the same. And so, cool, you're still going to have the same distance between you. That distance is going to be the same, even though that now you're going at a higher speed than you originally were. Yeah, and it's kind of interesting. But it gets to the question that at some point you're going to hit a finish line. And so let's say you both were just kind of running slow. This person crosses the finish line, and then, the time it takes you to cross the finish line, going at that slower speed, well, this time is going to be bigger. Cool. Compared to like, hey, you were both running, and then you're maintaining that same distance, but now you both were running real fast. That person crosses the finish line. Here, you were both running real slow. Now, the speed, the time interval when that person crosses the finish line and you cross the finish line, well, now that's going to be much smaller. And so that's what this problem kind of shows. It shows that, hey, if you both reduce your speed at the same time, this distance between the two cars won't change, but it will influence, the time the time where you cross into that next town. When that first car gets into that next town, you'll start a stopwatch, and that second car will take a certain amount of time. And in our problem, it's like, hey, you were going faster, making this speed, but then at some point you decided to go slower. So during the race, you were going fast, but then at the end of the race, both people really slowed down. You maintain that distance. And but both of the people, or in our case, the cars, are now traveling at a slower speed. Cool. And so then we just have that, you still have this 500 meters between. That first car will cross the finish line or get into that town, and the second car will have a speed of 11.1 meters per second. They'll have to travel 500 meters, and we want seconds to pop upstairs, so we're going to go 500 divided by 11.1. And that gives us 500 divided by alpha V. That gives us that 45 seconds. Cool. And I was just thinking that I could, from doing this problem, maybe I could come up with an equation for relative motion. But not on this one. You know what I mean? Someone would have to tell me the equation of relative motion, and I'd be like, oh, okay, aha, I get it. But I'm not going to go look that up. And so, this video is good because it's fairly simple, and it's the first problem in this book, this Olympiad book. And heck yeah, we can just kind of do it from intuition. And we can learn some things. But then if someone throws us an equation of relative motion, we can be like, okay, I get it. And then we can apply it to this problem. So cool. I'm just going to say the answer is 45 seconds. Because, and then the intuition is like, hey, both reduce their speed. And so when that first one crosses the finish line, the other one is just slower to get there. And so I know that the time interval between the arrivals of the cars at the second town during the bad weather, it won't be faster. It won't be the same. It'll be longer. And so 45. All right, so thanks for joining me on this one. And guess what? That's a video. Alright, hell yeah. So we're going to come back to this one actually, because I kind of looked up, we're going to do this kind of stuff, this velocity of something relative to something else. And so, yeah, this is kind of tricky. So we're going to have the starting line of this race. We're going to have car 2 right here, car 1 right here. And now we want to know, this is going to be before the storm. So this car has a velocity of 16.6. This has a velocity of 16.6. And now we want to know what relative velocity is. And so what we would say, and we're going to do this in 2 ways, because sometimes it's better to use letter notation. We're going to say this is car B, and this is car A. And we're kind of interested in car A, and so we're going to say, hey, what's the velocity of car A relative to car B? And this is one of those times where this might be the simplest problem where you can maybe just get to the answer. Like, what's the velocity of A relative to B? Also, it's called the velocity of A as seen from velocity of A. I don't know how you'd say that. Velocity of A as seen from A. Maybe you would say it like that. I mean, if you're in the car at A, and as a passenger, you look behind and you see car B. And what do you notice? What do you notice about car B? Maybe it's not moving. Okay, so I think that's the opposite way to say it, because we want to know what's our velocity. You know what I mean? So, and we're gonna get to that one in a second, where we're gonna do this little scenario, and we're gonna be like, well, if I'm at A, like, what is B doing? So let's just look globally, that we see the velocity of A relative to B. And so so I think this is saying, the way it's written right here, isn't this saying velocity of A as seen from B? So now let's imagine that we're in car B, you're a passenger, you're looking up ahead at car A, and is it moving? You know what I mean? In our scenario, it's not. So the velocity of A as seen from B is 0. Cool. Now for our problem, you're moving. Okay? So you're a passenger, but you look over at the driver and see your speedometer, and you're like, well, I'm going 16 meters per second. And just from intuition, I know that it looks like that car's not moving, because we know that we're not getting any closer, we're not getting any farther away. And so just intuitively, we know that car is going 16.6 meters per second. So we know, if you're a passenger, both cars have velocity. So how do we get 0? How do you take, So now, here's a great place to mess this up. You could say it's velocity of A minus velocity of B, or you could say it's velocity of B minus velocity of A. Both will get you there. One's going to be the right answer. One's going to be the wrong answer. So that's where you have to take. So if you're in this situation, take the problem to the extreme. So we're going to be in B. We're going to be in A. And now we're going to say, whoa, A just threw on their brakes. They're going 0 meters per second. But like, and you see that. You see that A threw on their brakes, instantaneously came to a stop, let's say. And you see the speedometer, we're going 16 meters per second. So right here, you know that you know your velocity. And so this is going to be tricky because let's write it, and then we know that we could write this, so we could write velocity of A as seen from B, or we could just write velocity of B as seen from A. And we're gonna first do the one that makes the most sense. So we have velocity of B, and we're still saying that this is the positive direction. So if you're in A and you look back, you're looking back to the negative direction. And so if you see B is going in the negative direction, you would say that that velocity is negative. But if you look back from A and see that B is going in the positive direction, you would say that velocity is positive. So, you know what I mean? And I'm being very slow with this because I don't know how you develop really solid intuition besides just playing around with, you know, how to say these, and then messing up, and then slowly, you know, getting a little bit better. Alright, so we have velocity of B as seen from A. And I might even be messing that up. Maybe you don't say it like that, but I think you do. I think you say, what's the velocity of B as seen from A? Well, it looks like velocity of B is going to be positive 16.6 meters per second. Cool. Now let's do this one. What's the velocity of A as seen from B? Well, now you have to, even though that you looked at the speedometer, you know you're going 16 meters per second, you have to assume that you're stationary, you know what I mean? So if you, you know what I mean, can't sense that you're moving, but then all of a sudden you see A, it looks like it's rapidly approaching you. So it looks like A is going in the negative direction. So it looks like velocity of A would be negative 16.6 meters per second. Cool. And I might even have to come back to this one to be like, well, what is the true scenario? You know what I mean? So that's where I did this little example where we have the starting line O, and then we have a couple points, and then we have a swing arm. You know, this is, we'll call this C, we'll call this point B. Point A is always kind of the one we're interested in. Point B might be the point that we know about. So this is kind of, I've been doing the MIT Dynamics course online, which anyone can take, but it's technical. And then we're going to say this is on a track. So this is kind of like a train on a track, and then it has this swing arm that swings. And so I'm going to say that this has 1 radian per second, and this is 1 meter. So the tangential velocity here, velocity of A, is 1 meter per second. And I'm going to say velocity of this, you know, the velocity of the cart, which is velocity of B, is going to be 10 meters per second. Cool. So now I want to do that same thing. I want to set up equations that says velocity of A, and we'll just do this one first. You know, even though we can do the full system, I'm just going to say velocity of A relative from B, or velocity of A as seen from B. And hopefully I'm saying that right. But yeah, I need to go back and watch those videos, because like, I don't mind making mistakes. If I'm making a horrible mistake, even just me saying this, you know, because the second you actually make videos and say words into sentences, you're just like, uh-oh. You know, don't take it as gospel truth. But what this is happening in my mind is right now, the next time I come across a lecture, you know, where the professor's like, hey, I have this, and then I say, like, velocity of A as seen from B, I'm definitely going to pay attention to that, and that's going to reinforce, and hopefully I'm right, and it'll reinforce that. If I'm wrong, then I do need to work on that and constantly, you know, make that correction. Okay, so let's try it. So velocity of A as seen from B. So if I'm at B, hey, maybe it looks like velocity of A is going forward. And let's write both these. Velocity of B as seen from A. So velocity of A as seen from B. So it looks like A is traveling in the positive direction. I'm going to say this is positive and this is negative. So cool, I'm going to say that's a positive 1 meter per second. Now let's do this. Velocity of B as seen from A. Well, it looks like B, like, hey, if I'm on A and I'm riding this forward, I can't sense, that's try to stop stuttering as much. I'm going to bring that up. In Newtonian, physics, one of the concepts is that if you're on something, like an airplane, if you're in an airplane and you're going at a constant speed, you just can't tell that you're moving. So always come back to that fundamental, that I could have velocity at A, and I do, I got tangential velocity, and I just can't tell I'm moving in this direction. And sure, we're swinging, and so we know that we're going to be forced to the ground, but that would be no different. I mean, if this is a space station, it just feels like you're on the surface of the ground. You still can't tell that you're moving in that direction. So even if you have a huge space station that's just floating out here, you're on the bottom of it. It's so big you can't tell that the walls are even curved up. You feel some gravity because you're spinning, but you won't know that you're spinning. You won't know that you're traveling that way or that. Oh, so that's wicked. You know what I mean? This thing could be spinning that way or it could be spinning this way, and you won't know. You know what I mean? So that is fascinating. And I think, so cool. So leave it at that. All right, so let's go back to this one. Velocity of B as seen from A. Cool. So it looks like, even though I'm traveling forward, it looks like B is traveling backward. So I'm going to say B is traveling negative 1 meter per second. All right, hell yeah. So, I think we need a new sheet of paper. I'm going to redraw this one, though, because it's fascinating. We have O, point C, point B, and then point A. And then we have this on a track. This can go 10 meters per second. Okay, so, and then in general terms, what's the relative velocity between A and B? Like, what are some things that, and we're going to say this is spinning this way, and we do have a tangential velocity of 1 meter per second. But we could say that if you're at A, it looks like B is moving backwards. So I could say that, let's see, we're going to call this A and this is B. So I could say, hey, it looks like A is moving 0, but B is moving negative 1. And then also I could say that A, is going positive 1 meter per second and B is stationary. So those are kind of the two scenarios I can have. I can't have one going 1 meter per second and the other one going 1 meter per second the other way, because then you wouldn't perceive that. It would look, if I was going 1 meter per second this way and this was going 1 meter per second that way, seen from A, it would look like that's going back negative 2 meters per second. So that's the scenario that we don't have. It just, from one point, you can't tell that you're moving. So you're basically the stationary point, but the other point's going to be moving. And then, but just globally from the problem is that, hey, if I know point A is moving this direction, but if I'm on point A, I can't sense that. And so it looks like point B is moving back the other way. Cool. So I'm just going to divide, this is something that we do, I think this is why I'm so slow to go over this. Because something that we do in physics all the time is take the difference between these. And I think I'm going to strike out on this one. But I'm just going to say, what's negative 1 minus 0? Yeah, that's why I kind of want to write these the other way. So I'm going to say B, A, and I'm going to do negative 1, 0, and then 0, positive 1. But let's do this one. So we have B minus A is negative 1 minus 0, that's negative 1. Then we have 0 minus positive 1. That's going to be negative 1 as well. Cool. And then if I come over here and do that same thing and take a minus b, we're going to have 0 minus negative 1. That's going to be positive 1. And we're going to have 1 minus 0. That's still positive 1. And then so what I don't even know, you know what I mean? But can we say what we just did? I don't even think so. Alright, so I do know that this part of the problem gets kind of confusing. So I'm going to make B a fixed point, you know, fix it to the ground, and then we have a swing arm coming down to A. So now the same situation applies. We know that B is not moving. Velocity A is 1 meter per second. But the relative velocity is this as seen as. If I'm on A, it looks like B is going negative. And if I'm on B, then it looks like A is going negative. So, yeah, so this, yeah, that's kind of interesting. Alright, so I threw myself for a loop by even writing these because I just don't even know if they apply. So let's go back to our relative velocities. We have velocity of A as seen from B. So I'm going to be at B, stationary, and I'm going to see that we're going plus 1 meters per second. Velocity of B as seen from A. So if I'm at A, it looks like B is traveling the other way, meters per second. Oh yeah, finally, this is the other, okay, so I know that these are equations that get used in physics, but also I can just say velocity of A is 1 meter per second. You know, check that box. And velocity of B is 0. So if I know that these two things are true, how do I get this? You know what I mean? So this is like back to my solution of like, hey, the units are the equation. If I got meters per second, and then I have seconds, I just multiply those, you know, and I get something useful, meters. And so if this is my something useful, all right, hell yeah. So if this is what I'm trying to get, and these are the only two things I can use, well, cool. It looks like I have to, well, I could either add them. I could say velocity of A plus velocity of B. That's going to be 1 plus 0 is 1. And I guess I could subtract them. I could do it in this order. I could say velocity of A minus velocity of B is 1 minus 0. And, you know what I mean? So I'm still, you know, maybe I'm still unsure about which one to use. Alright, hell yeah. So let's just start off with some scenarios. So what I'm going to do is I'm going to have this starting line, and then I'm going to have A out here. And I have velocity of A is 1 meter per second. And so, so I know that velocity of A is 1, velocity of this starting line is 0, and velocity of A as seen from O is definitely going to be, as seen from, it looks like A is going to be positive 1. Okay, so I could still have that same scenario, you know, so I don't get any closer. But I did write this just because we can say, hey, let's say, so we're gonna say this. We're on a train that has a flat track, and this is, and then the starting line was over here. So this is O. And then here is A on the track. It has a velocity of 1 meter per second. But this track has a velocity, let's say, of just 2 meters per second. And then we're going to call this point B. So this is kind of how you do it. You pick a point on the thing that's moving. This is your classic. You have an origin. You have the velocity of the thing that you're kind of analyzing. You have the velocity of something that's known, you know, like on the track. And then usually your fixed point has no velocity. And so we could say the velocity of A is 1. The velocity of B is, oh shoot. No, you can't say that. Because those would be absolute velocities. Because, oh yeah, even back here, these are absolute velocities. So we know that B is not moving, A is moving 1 meter per second. But the second we introduce something else, we're just like, okay, so absolute velocity A we can just see is 3, and velocity of B is 2, and I guess you could say velocity of O is 0. Yeah, let's rewrite this one. Alright, hell yeah. So hopefully this goes somewhere. So yeah, velocity of A is going to be 3, velocity of B is going to be 2, velocity of O is going to be 0. And so let's start writing our relative velocities. We could say velocity of A as seen from O. Cool. So as seen from O, we know that's going to be 3. And then, but why is it going to be 3? Well, it's going to be 2 plus 1. I think we can see that. We're obviously not going to subtract anything. This velocity is 0. This velocity is 2. This velocity is 1. So we know that velocity of A, as seen from O, has to be, well, how would you write this? Alright, hell yeah. So back at it. Man, this stuff sucks, but we're doing it. So yeah, so this 2, where this comes from, like we know it's hey, it's the absolute velocity, but that's just relative, to the Earth. Let's say this is the Earth, and this is just, our starting point for this train to go down the track. But hey, like if we're on the equator and we're looking, if this is the South Pole, I think I got this right. So if we're, I don't know, but whatever. Well, if it's the North Pole down here, we're looking kind of down on the northern, on the top of the Earth. Hey, the Earth is going to rotate that way. And so, like hella fast. So actually, this velocity is going to be, and we're going to, let's say we call that the negative direction. Well, cool. This is going to be negative hella plus 2. And this is going to be negative hella plus 1. So this really shows that you're just like, oh, okay, because I thought from this picture, like 2, this seemed pretty like substantial, and like fixed. Like, hey, this B had a velocity of 2. Well, now everything in the universe is moving. So yeah, it really shows this idea of relative velocity. And I mean, I'm glad I'm spending time on this, because this is up there. Like, the relative velocity is one of these tricky things that it melts my mind. And, so you have relative, and it's the foundation of dynamics. And it's the hardest thing in dynamics. I swear, when the professors go over this in the lecture, you can just tell the students have a hard time, keeping up with these relative. You have like, hey, the velocity of B, but yeah, relative to what? Yeah, velocity of B relative to O. Okay, so that little sidetrack was what I was, getting at. So we have this 2 is velocity of B relative to O. Sweet, so I can say this. What I thought that these were kind of absolute velocities is this is velocity of B relative to O. Cool, so what's this 3 though? You know what I mean? Because I can't just, is that velocity of A? Well, yeah, isn't that just velocity of A relative to O? For relative to O, I think A is going 3, so that's a check on reality. Okay, but isn't velocity of A like anything else? Sure, we can have that term velocity of A as seen from B. So if I'm on B, hey, it looks like A is going to have positive 1 meters per second. So let's write these in. This is 3 meters per second. This is 2 meters per second. Alright, and then just kind of one of my tactics is just like, well, I see 2 things that add up to 3. Now, are those 2 things related? You know what I mean? So this is what I do all the time. I was just like, well, this says 1, this says 2, this says 3. And I don't have a 3. I didn't write a 3 down. So I must have added these 2 things together. So is that going to be true? Velocity of A as seen from O, is that just velocity of B as seen from O plus velocity of A as seen from B? And I'm just going to go with it and say yes. And let's see. All right, hell yeah. So now I'm full circle. Cool. So I just said velocity of, and I think this is going to work. So let's just put that aside for now. The other thing that I know is like, hey, the absolute velocity of, damn it, I had it. All right, hell yeah. So what I want to do is write the other term, velocity of B relative to A. So we said velocity of B as seen from A. So if I'm on A and I don't think I'm moving, it looks like B is going that direction, and as much as I'm moving this direction. So booyah, it's going to be negative 1 meter per second. And this, cool. Alright, hell yeah. So let's go over this. So we have velocity of A as seen from O. We just know that that's, just from the picture, we just know that that's 3 meters per second. We know velocity of B as seen from O is 2 meters per second. These are kind of our absolute velocities if we're taking, O to be like our established reference frame. We're not going to take in the cosmos and the moon, whatever. But now we have this term, the relative velocity term, which we said velocity of A, if we're looking at it from B, it looks like this is going to be plus 1 meter per second. And so sweet, we have this. But now we have an equation that works. Now we can rearrange this. So let's do this. Let's have this velocity of A as seen from O, or with respect to O. And we're going to subtract this side. Minus velocity of B as seen from O is the relative velocities between them. And then let's talk about that. So we have velocity of A as seen from O. So yeah, we're going to be going 3 meters per second. And then we're going to subtract the velocity of B as seen from O. That's 2 meters per second. And the quantity that we get is the relative velocity. So this was 3, this was 2. So we get that positive 1 term. And that would be, the only way we're going to get positive 1 is if we're on B and we're seeing A move in the positive direction. So this is going to be velocity of A as seen from B. So that's what we would get, and that's what we see right here. Cool. So now let's just do the second thing. Let's say we have velocity of B as seen. We know that the absolute velocity of B as seen from O is 2. And so let's subtract 2. Let's subtract that. So we're going to go 2 minus velocity of A as seen from O. And that's going to be subtract 3. And what this would give us, I don't even know why you would do that. Yep, I don't know why you do that, but what you get is you get 2 minus 3 is a negative 1. And what you would, and the only way to get a negative 1 is if you're on A and it looks like B is going the opposite way. So we can say velocity of B as seen from A is going to be velocity of B with respect to the origin minus velocity of A with respect to the origin O. So that's going to be negative 1 is 2 minus 3. And I guess it's an equation that works. All I'm trying to do is like say right things. And obviously, some just kind of makes sense that if we have the total velocity of A minus B, then that's going to be relative what A is. So if this track is moving 1 meter per second, like our problem, both the cars are moving at the same speed, which just means that, oh, just a second. Yeah, sorry. What I'm saying is that these are the absolute velocities. So I'm saying this is velocity of B relative to O, and I want velocity of A relative O to also be 1. But we know if this is a train and the train is point B, that the velocity of A relative to B has to be 0. So, and the velocity of A relative to B is it stationary? It means that what this term means is that when the car is on this train, you didn't turn it on, it's just stationary. So, I mean, this stuff is sucky and very difficult. Because it's just like, hey, if I'm on the earth and I'm in my car but not moving, the velocity of A, this point A relative to, the starting line right behind me, point O, that's going to be 0. And so, but the second we change this reference frame and say this is no different than just being on a flat train, and I'm just going to say that this is let's call it point O again, you know what I mean? And we can just do that. This is point A, velocity of A relative to O, stationary, no velocity is 0. And then there's no difference between changing this point O just into point B. I think that's kind of the hardest thing about physics, is like you can make these points any letter you want. There's nothing special about O being used for the origin. It's just a letter. So this would be the velocity of A as seen from B. It's also 0. So a stationary car on a train, and let's say the train's not moving, but the second we move this train, so now let's say the train, and I'm saying point B is on the train, so I'm going to say, and then I have to, if I say the train is moving to what? You know what I mean? Because any sort of velocity you wouldn't be able to tell. The only way you're going to be able to tell if the train is moving if it's on an earth that appears stationary. Cool. So now from the starting line of the train station, I'm going to put that as a letter, and we could choose we could choose this Z, you know what I mean? But let's stick with O. And so now we know that velocity, like the velocity of A, you know what I mean, in an absolute sense will have, and we're going to say the train is moving at 1 meter per second. So we know that velocity of B in an absolute sense is 1 meter per second. The car is still stationary. Velocity of A in an absolute sense is also 1 meter per second. All right, but we're going to take it home, you know what I mean? But what does this mean? Like the train has a velocity of 1. Like relative to what? You know what I mean? So that's like I could make a shirt that says relative to what? Just because it's like how do you know that you're, and it's so interesting because that's what physics is cool. It's like, prove it. Like, do you know that you're moving on this earth? It's like most people, it's like, no, not really. You know, that's why you just get crazy theories that like the sun is just like northern lights, you know what I mean, every day, where there is no motion. It's just an optical illusion displayed in front of your eyes, where it's just like, cool. Like you have to prove that you're having motion, and motion is very difficult because we don't sense it. It doesn't feel like I'm moving at 1,000. I'm at 45 degrees latitude, so it doesn't feel like I'm moving at 700 miles an hour, around the Earth. So yeah, it's relative to what? So in this case, the train is moving relative to the train station at O. So we would say velocity of B relative to O is 2 meters per second. And then we would say the velocity of A. It's also, we were trying to choose 1 meter per second for the train. So the train is moving at 1 meter per second. But we also know the car, is moving at 1 meter per second relative to the train station. Cool. We want the train and the cars on the train to be moving at the same velocity, because if they weren't, the cars would fall off the train if they started to roll back or roll forward. So cool. So that's where this term, it looks like an absolute term, but it's still relative to this point. And then relative to what? Because this point is only relative to another point. And some problems, especially involving Coriolis, you have to take a point that's kind of fixed. Oh, that's so fascinating. Like, I don't even know. Like, is it wise to take the center of the Earth as your, do you need to take the center of the Earth as your fixed point for like Coriolis effect problems? That'll be something for me to think about. Okay, hell yeah. So did I learn anything? You know what I mean? So I have these absolute velocities. So let's do this train where and now I want to know the relative velocity. So I know velocity of B relative to O. Cool, that's 1 meter per second. And I know also velocity of A relative to O is 1 meter per second. But what connects B and A? Like again, like let's say the train is just the earth. Let's get rid of the wheels. And then I just have a stationary car over here. And then I just pick some arbitrary point B. And I want to know what the velocity of A is. Well, I kind of know it's 0, but how do I designate that? I say velocity of A as seen from B. Cool. That's going to be the velocity in this positive direction, and it's 0. Cool. So and now let's put the wheels back on, and then here's the train station. And you know, how would I, if I know, like, how would I find relative velocities? I have no idea. Alright, no, I got this, and we finally get the difference, and thank goodness, because I know that the relative velocity is kind of this general sense of velocity of A, but minus velocity of B. That's going to be the relative velocity between B and A. That's going to be the two people in the race. You know, if they have a difference in their velocities, where this person's catching up, you know, it's as if this person stopped and this person is just slowly like walking towards this person. So that's the same thing. Even if you're in a race and both people are actually going pretty fast, but this person's just going a touch faster, it might take a while, the whole race, for this person to catch up, pass, and win. But in a relative sense, it would be weird, you know, because you would just get 20 feet behind a person, and then over the course of maybe 20 minutes, you would just start slowly walking towards that person. And so that is just a bizarre thing. But that is your relative velocity. During that race, if you're catching up and winning, your relative velocity, you know, if this is, if you're B and this is A, well, in this case, yeah, let's do it. And if you're B and this is A, you know, I mean, your velocity of B as seen from A, and this is going to be the positive direction. If you're A, you look back, it looks like B is going in a positive direction. So this is just going to be positive 0.1. You know, I mean, it's kind of a small number. Holy Toledo. So that would be the same case as if this car started to roll backwards. And let's say it just rolls backwards at a speed of 0.1 meter per second. Cool. So let's do this one and be done. I'm just going to get slowly. I'm not gonna master this the first time, but is the only way that I'm going to get better is just to experiment and try to say right things. Hopefully say a few wrong things, and then observe why I'm saying those. Okay, hell yeah. So train station, the train's going 1 meter per second. All of a sudden this car is starting to roll back, and I want to know the relative velocity. And in this case, like maybe, like in this case I was interested in B, like how far B was, the speed of B in the positive direction winning. In this case I want to know the velocity of A relative to B. Yeah, so that's right. So if I want, I know the velocity of A is in the negative direction. And so, hell yeah, I see that. So this velocity, it's still the velocity of A. So we still have A going in the negative direction, and the relative part is as seen from B. So let's do both. Let's see velocity of A as seen from B, and velocity of A as seen from the train station. And we know from the train station, well, this whole thing is going 1 meter per second. Everything's going that way at a faster speed, and then this starts to roll back. So I just know that this is going to be 0.9. And this is the way to do these problems. Like, come up with something intuitive where you just know the answer right off the bat, and then figure out why that is with the equations. Velocity of A relative to B. This one might be a little bit harder because you're just like, well, I don't know. But we can see that's going to be negative 0.1 meter per second. So let's figure out why this is. So we would say the velocity of A as seen from B. Why is it going back in the negative direction? I think that's going to be the velocity of A as seen from the origin minus the velocity of B as seen from... I think it's going to be the difference between the two velocities. Now, am I right about that? I don't think so. Let's do this one then. Velocity of A as seen from this origin is going to be, yeah, this is where I'm pretty bad. I just know from the actual problems is like, hey, we know this train is kind of one of the reference frames. We know the Earth is the, and I'm starting to use the actual terms. We know that the Earth is the inertial reference frame. It's the reference frame where the problem makes sense regardless. Like, we actually have a reference frame where the problem will always make sense. It's not a Coriolis problem where you need to choose a reference frame wisely. Holy hell, I feel like I'm just saying words. But, okay, so, yeah, but this point B is a moving reference frame. So, cool. And so we say, so you start from here, get to your moving reference frame, and then figure out what's moving on your moving reference frame. So we can say velocity of B relative to the inertial reference frame. That makes sense. And then we're going to, is it going to add or subtract? I have no idea. Who cares? But we're going to say now the velocity of A, the thing that we want, relative to B. Cool, I think we have it. You know what I mean? We start from here. We want to know the velocity of B relative to this point. We move to this point. But now we really want to analyze the velocity of A relative to this point. And so this is the classic way to get an equation. If you're like, hey, what is the velocity of A relative to O? And this is what happens where, and this is cool. Wow, this is such a struggle. But the only way you're going to be able to teach this is to say it and see if you're saying wrong things. But in problems, you're going to be like, well, I don't know this velocity in terms of this point. I only know the velocity in terms of this train. I can see that it's moving back. But I have no idea relative to this point. You know what I mean? So that's why we have to go from here to there. And then once we're here, we can go from here to there. So this is the classic form of the relative velocity equation. We want to know. I mean, for sure, this is the thing that we're analyzing. All right, hell yeah. Sorry about that. Switch batteries. And so, cool. We have the relative equation. We want to know A. We're analyzing that. And we want to analyze it in terms of, this point O. And so we have to first figure out the velocity of something we do know, velocity of B with respect to O, and then we have to say the velocity of A as seen from B. Cool. And then actually do, you know what I mean? Like say this out. We're going to be at B, and what is A doing? It's moving in the negative direction. And that's the other thing. Is like we set this coordinate system, and and maybe I'm actually making a mistake right here. Like when because you can have two different coordinate systems too. Like that's the other bizarre thing. Is like I might only know this thing might be rolling down a hill. Yeah, that's bizarre. This thing might be rolling down a hill at an angle like this, and A is still I don't know. You would have to say it's going up a hill. Yeah, let's do that. So we have the train going up a hill, and that's why this car starts to roll back at 0.1 meter per second. And then here's our train station out here. Well, I'm just going to say just right in line, and then we go up the hill. And then here's our point B. So we would have, but in this case, hey, look at this. Our velocity of B with respect to O changed a little bit. You know what I mean? Because if I know that the engine, yeah, you almost need a couple, you know, you would need, maybe you would have, maybe O is right here, and then you have point C right here. All right, this is pretty cool. We're gonna come back to that one. But yeah, so, yep, and then, yeah, so let's talk about this relative term. So we're analyzing the velocity of A as seen from B, and we see that it's moving back negative 0.1 meter per second. Cool, so we're going to have, we know that the train is moving 1 meter per second minus 0.1, and we get that 0.9 meter per second. So that seems simple, but holy Toledo, it seemed like if we put, if we have the train station, point C, because now we have a hill, and now we have our train, and then we have a car on the train that's going to roll back at 0.1 meter per second, and we're just going to have a 30-degree angle right here. Sorry for scribbling this out. Now we want to know velocity of A as seen from O, and so what we're going to do is we're going to be like, well, hey, what's oh yeah, this is interesting because this is a different reference. Like if we set this as positive X and positive Y, this might be for another video. I don't even know why I'm doing this. Positive capital X. This is going to be positive capital Y. Sometimes they do that. If you're going to do two frames of reference and you still want to use X, Y, X, Y, but you don't want to use primes, just use capital X's and then maybe lowercase x's and Y's right there. I'm totally going to strike out on this one. But I still can go from C. You know, like, let's forget about this frame. But from C going up this hill, I can say velocity of A as seen from C is, and I'm going to say this is point B. I'm going to say it's the velocity of B, the train, as seen from point C, the bottom of the hill, plus the velocity of A as seen from B or relative to B. And that's going to be in the back direction. So maybe I'd have 1 meter per second here, and then negative 0.1 meter per second. So I still get that 0.9 meters per second. But if I wanted, let's try this. Velocity of A as seen from O. And this is maybe where you actually have to do, I don't know. Let's see. I don't even know what complicatedness you'd have to do. All right, booyah. So we're going to have velocity of C with respect to O. But that's where these are... Oh, I see. We were just doing velocity in one direction. So the second that we have, you know, two directions, now something's traveling this way with the velocity in the X, and maybe it has a velocity component in the Y. These have to be vectors. Cool. So yep. So we would have velocity of A as seen from this point is going to be the velocity of C from this point plus the velocity. And so the velocity of the bottom of the hill doesn't change. You know what I mean? So I can see that right now. It's like, well, doesn't the bottom of the hill have zero velocity? Why would you even put that in? You know what I mean? Cool. Maybe we should have just put our reference frame right here, which we could. But if you're still going to have it in this direction, you know what I mean? Yeah, it's going to be different than angling the reference frame. Okay, so let's still keep it from this point. So velocity of C relative, the velocity of the bottom of the hill as seen from over here at the train station, the bottom of the hill is not moving. Cool. All right, but now we have velocity of the train itself relative to the bottom of the hill. Okay, so that is moving. And this is where you're like, oh man, I don't want to do this, but I should, just because it's good practice. This is for a different video. But I would say I can see that this velocity of the train is just 1 meter per second in that direction. This is going to be a 0.1 meter per second in the negative direction. But those are going to be, and then this is where these are vectors. You know what I mean? Well, the coordinate system isn't a vector, but then you actually put a unit vector in that direction. If this has a magnitude of 1, this has a magnitude of 1, and you would say this is capital X hat, and this is capital Y hat. Over here, same thing. If your unit vector is just this long and this long, sometimes it's useful to make your unit vector as long as, like, you know, as long as you want. Just make sure they're symmetrical, and we would have y, lowercase x hat, lowercase y hat. All right, so cool. So you'd have velocity of b as seen from C, and yeah, you do have a vector on it. We'll get back to that in a second. And cool. Now we move to this point, and now we can say the velocity. Now we want the velocity of A as seen from B. Cool. So we just did the same thing. We started at O. What's the velocity of C relative to O? What's the velocity of B relative to C? What's the velocity of A relative to B? And yeah, we just moved up. At the end, we wanted to analyze point A. And if we move back, we're saying, hey, I want to analyze A as seen from B. Okay, we're moving backwards. But then I want to analyze B as seen from the bottom of the hill. We're moving forwards. And then I want to analyze the bottom of the hill as seen from this origin, not moving. Cool. But if I'm going to, so I'm going to say this is 0, but if I'm going to say that this B, the velocity of B as seen from the bottom of the hill is going to be plus 1 lowercase I hat, you know, and then plus 0 y hat. That's going to be this velocity. It's going to have two components. No velocity in that direction. Velocity of 1 meter per second in this direction. And then now we're going to come over here to A. A is going to have negative 0.1 if this is the lowercase x hat direction. We're going to have negative 0.1. It's not going to have any velocity in the y directions, plus 0 in the y hat. Cool, but you know, this coordinate system has coordinates in the x big hat, capital Y, you know, no one calls it big hat. Maybe I will. But capital X hat, capital Y hat. All right, let's grab one sheet of paper. We're almost done. But this is the suckiest part, and this is like the part where no one wants to do. Is just like how do you get from this vector? I mean, because all we have right here is velocity of A relative to O is 1 lowercase x hat minus 0.1 lowercase x hat. That's going to be that 0.9 x lowercase x hat, which is what we thought we were going to get in the beginning, but that's in kind of this direction. I want to know relative to, I want to know in terms of these coordinate systems. And so so just back from statics, you're like, well, I have a vector at a 30-degree angle, and it has a quantity 0.19. Cool. But I chose this direction to be my vector. It doesn't really matter. But what I want is I want its components in this capital Y hat and then capital X hat, which is just right there, and it's just right there. So I would say it could be very useful to kind of model this with a picture. And I feel like I'm even forgetting something, but I'm not. The only thing that I'm forgetting is that this is plus 0.0 y hat. Because usually if you have a vector in a coordinate system, you know, we chose this as our coordinate system, but it was just all in one direction. Typically it's not. Like you're going to have this tilted coordinate system, but then you're going to have some maybe resultant velocity that way. So it's going to sure have a component in this lowercase x hat, but it's also going to have a component in the lowercase y hat. So you would have another term here. And yeah, you would have this term this way, and then maybe at a 90-degree angle, you would have this term that way. And you would have to find the components of each of these. And then once you did find the components of each of those, both are going to have a capital X hat component and a capital Y hat component. And both vectors are going to have that. And then you're going to have to add these up to get one vector that just has a capital X hat and a capital Y hat. So it's for this, I don't know. I don't think there's anything worse than going through a bunch of difficult stuff and then just having, this is such a painstaking and there's no other easy way to get to do it. It's bizarre that there's not. You get lucked out when your tilted direction only has one component, because we're going to have 0.9, and now we can just draw it. We're not going to have that one, so now we just have one, and we just want to know this. And if you do it visually, you're like, okay, I can deal with it. It just sucks when you have something like over here. Let's say we did have this vector. You just have to figure out, so this is a 90. What you have to do is be like, well, I know that this is 30, and then so I would say this is 90 plus 30. This angle is 120. And then you just need to know that in your calculator, sines and cosines, if I throw in 120 for sine and 120 for cosine, let's talk about that. My angle is here, and so, it's bizarre. Let's talk about this, because I usually just do like a 30-degree angle. Sun is shining on the sine end, but this is the one place where that rule does not work, and it's for obtuse angles. So now let's do the 120. Like this is 30, but this whole thing is 120. So what's the sine of 120? Well, it's going to be this vertical direction. And so even though you have a sunshine, it's not really shining on any vertical component. But then I would always start, hey, if this is my baseline 0, and then this gets overlooked. It doesn't matter where you start your baseline. I could say this is 0, and this is the positive 90. Cool. But that means that this has to be the positive direction, this has to be the negative direction, this is positive, this is negative. Typically what you'll have is this is positive, this is negative in this direction, this is positive, this is negative in that direction, and then your angle will have to be this direction. So if you're going to take an angle from this direction, you can get to whatever over here, and this is going to be the sine component, the vertical component of that angle. And this is going to be your cosine component. So yeah, so over here, the cosine of 120 is that length. It's a negative length. The sine length is positive. But then when you rotate all the way around over here, you know what I mean? Your cosine component is going to be positive, and then your vertical component is going to be negative. All right, so that's just kind of the trickiness of using that equation. All right, booyah. So let's finish this one. So we have, and I'm just going to redraw this axis. So we have that 30 degrees. This is going to be x prime. And then we have this y, lowercase y. I want it in the capital Y, capital X. I know that this is a length of 0.9. And so, what are these components? This is going to be 30 degrees. So, this component is going to be 0.9 cosine 30. Sun is shining on the sine end. The adjacent is the cosine. And so this is going to be capital X. And it's going to have a y component of, and it's going to be positive 0.9 sine 30. So sunshine and sine in. Your hypotenuse is 0.9. Again, sines and cosines are just percentages of the larger number. That's the hypotenuse. That's what I think about sines and cosines. And if I know the hypotenuse, I can take the percentage of the hypotenuse, either the sine or the cosine, and I can get that vertical component or the horizontal component. Now, it doesn't have to always, the sine doesn't have to always be the vertical component, especially if you're going to take your angles from the vertical direction. All you have to do is start here on one of your vertical things, and I'm just going to say, hey, I'm going to go this way with my angle 30 degrees. Cool. So now my sine component is a horizontal component. This is going to be 30, sun is shining, but the sun is shining always on the sine component. So yeah, turn your angle, put some sunshine rays, and those are going to shine right on that sine component. Okay, hell yeah. Yeah, it's so dumb, but I think I'm the only one that actually says sun is shining on the sine. And one of the professors online that does the statics, man, it gets annoying where he just says like, he does it's so interesting. He does like load diagrams where you have shear and moment. And then so if you have all this, if you have load, I have no idea. Let's do this. Yeah, you have a beam and then you have load here. You're going to have half and half. Your diagram's going to be up and then down and then like that. And so you go up and then down and then. But anyway, so he does the moment. He's just like, well, you're skiing. You know what I mean? Where you're like, are you adding? You're going to add. Are you adding big stacks? Let's see if I can even do it. He said something about adding big stacks and skiing, and he says so. Are you adding? So I haven't added anything, but then am I adding? Oh no, it wasn't that. It was. Let's do this. So it was. Sorry, I'm just on a tangent. So it was a beam with distributed load downward, and then so you're still going to take half here and half there. So your shear diagram is going to be up, and then but then continuously down, and then up. So that's going to be different than a beam where it's loaded right here. You're going to, have half and half, and so your shear is going to be up, over, down, over. So, but when you have it like this, what's your moment diagrams? And he said, like, hey, are you adding big stacks? And yes, you're adding big stacks and then adding little stacks. And so he equivocated adding big stacks. See, it's so wild how I can remember that. And so all I'm saying is like sun is shining on the sine, and how can you not remember that? But I did show a way, sorry, a little ADHD. I did show a way where if your angle is obtuse, yeah, the sun isn't shining nowhere. But if I start with a smaller angle and see that the sun is shining on the vertical component, when I get to 120, an obtuse angle, the sine and component is still vertical. Where if I'm in the vertical direction, I do a small angle, sun is shining on the horizontal component. If I take this angle to an obtuse, so now I'm at like 135 degrees, the horizontal component is still the sine component. So sun is shining on the sine component is horizontal. So let's go back to this. It's kind of a fascinating one. So if here's your shear diagram and you're adding big stacks, it means that your moment is a steep slope. And so you have to start at a steep slope, and then you have to start, and then here is like a baby slope, or like a beginner slope where it's flat. And so that's what your moment diagram is going to be. Once you get to here, hey, you're going to be the opposite direction, and you're adding, and you're not going to be adding big stacks. Small stacks, then big stacks. So you're going to go shallow and then steep. And it doesn't matter, like, he calls it skiing, where, like, obviously you're not going to ski that way, but you can just imagine, that's the only part of the analogy that doesn't work. It's not always a downhill ski slope. You're not always being like, oh, steep stacks to little stacks. Because if this is in the positive direction, your moment's going to be positive just by convention. But then once this is negative, you're going to be going to the negative. I just thought that was a creative way, and oh man, ADHD is getting the hold of me. But no, it's just kind of fascinating. Like, no, I shouldn't say that. You know, I just enjoy doing this, and it's just fascinating how to get better to be a learner, how to get better to be a teacher. So what the hell did we do? This was the equation. So if I had velocity of A, so I wanted to know, like, where's the picture of this? I don't even know, like, where my train is. Yeah, so here's my train at an angle, and we got our equation. So we have the velocity of A as seen from O is going to be 0.9 cosine 30 plus 0.9 sine 30, and it's going to have you know, in this x direction, I'm just going to call this I hat, j hat. There you go. So this is your capital X is your I hat, capital Y is your j hat, and cosine 30 is going to be 0.866. And does that make sense? Like, hey, this is almost 0.9. It's 85%. Cosine 30 is 0.866. Good one to know is just 86.6%. You can round it to 100 if you want. This dimension is about the same dimension as that, a little bit less. But cosine 30 times 0.9 is, oh, damn it. Cosine 30. What was cosine 30? Oh, I'm in radians. Sorry about that. Cosine 30 times 0.9. So we have, so our final equation is the velocity of A as seen from O is 0.78 meters per second in the I hat plus half 0.45 meters per second in the j hat, because sine of 30 is 0.5, 50%. And yep, just to show you that one, if you have a 30-degree triangle, hell yeah. This is your hypotenuse. It's the larger number. Divvy it by 2. You know what I mean? That's about the same length as that. So that's always good to do. All right. So I think I did what I wanted to do.